What makes up the universe and how does it evolve? These are questions that scientists have been asking for many years, if not thousands of years. A step, hopefully, in the right direction is the theory of dark matter and dark energy. Scientists have been studying galaxies and galaxy clusters for many years and have discovered that the calculated mass of the universe is a lot more than expected. The theory of dark matter and dark energy came about because of this. There must be some form of matter that is there, but we just can't yet detect it. The stretched light pieces on the right, a part of the picture of a galaxy cluster called Abell 370. Those stretched light pieces are actually snapshots of a galaxy behind Abell 370. Evidence for dark matter. I'm going to focus on 4 pieces of evidence just for this presentation, although there are more. The first one, galaxy rotation curves, along with velocity dispersion, galaxy clusters, and gravitational lensing. The evidence for dark matter. First, galaxy rotation curves. Scientists have been calculating the velocities of galaxies and the motions of these galaxies. The rotation curves of spiral galaxies indicate that there is too much mass, meaning substantially more than the summed masses of the galaxy's stars and gas. And 2, the mass is not distributed like the stars. It's more spread out. The extra mass is not even in the same place as the stars. This provides strong evidence that the luminous mass alone cannot account for the observed dynamics of the stars and gases in a spiral galaxy. On the right is an image of a spiral galaxy with luminous mass concentrated at the center. Obviously seen is the brightest portion is at the center. The velocity should decrease as the radius increases. Where there is less mass, the velocity should decrease. But this is not what is observed. In spiral galaxies like the Milky Way, we calculate the gravitational mass from observing the motions of stars and gas clouds in the disk as they orbit the center. The rotation curve of a galaxy shows how the velocity of stars around the center varies as the distance from the center increases, as shown on the left. This is a plot of velocity versus radius for a typical spiral galaxy. The dashed lines are what we would expect, what we thought we would find, and the black line up at the top is actually what we measured, with data points along that line. Most spiral galaxies show flat rotation curves, even where no more stars are visible. Therefore, we conclude that the gravitational mass is much more massive than the luminous mass. There's actually mass increasing as you move outwards from the galactic center. The picture on the right shows exactly this. The yellow portion is what was measured, and green was the theory, what we thought we would expect for rotation speed and distance from center. The next piece of evidence for dark matter is velocity dispersion. This picture shows different stellar kinematics for different galaxies using the Hubble sequence in the Khalifa survey. General properties and aperture corrections apply. The different colors represent different velocity dispersions. Stars in bound systems, like these galaxies, must obey something called the virial theorem. And this theorem, together with the measured velocity distribution, can be used to measure the mass distribution in a bound system, such as these elliptical galaxies or globular clusters. As with galaxy rotation curves, the obvious way to resolve this is the existence of non-luminous matter. Evidence for dark matter, the next piece, is galaxy clusters. On the right is a large-scale distribution of galaxies to a radius of about 650 megaparsecs, and we place ourselves, the observers, in the center. Each dot is a galaxy. As you can see, there are many, many dots, most of them being red ones, indicating red galaxies. As you can see, if you look across, there is an obvious distribution and large-scale structure to it. Their masses can be estimated in multiple ways. Galaxy clusters are gravitationally bound to each other, hence why you see this structure. Applying gravitational lensing to determining the mass will help us. Gravitational lensing. Light from a galaxy behind the cluster goes through and becomes distorted. We know many different forms of lenses in our everyday lives. Our glasses, magnifying glasses, microscopes. And when you look through a lens, that image you're looking at gets distorted in some way. That is what's happening here with gravitational lensing. The cluster is acting as the lens, and light is coming from behind it and going through it and becoming distorted. On the right, this is Abel 370. It shows a collection of more distant objects being lensed by the combined gravitational pull of a foreground cluster of galaxies. The distant lensed galaxies are seen distorted. We can study the amount of this distortion and determine the mass of the cluster itself. By measuring the distortion geometry, the mass of the intervening cluster can be obtained. Here is another picture describing more in detail what gravitational lensing is. As you can see on the left, that is the observer on Earth, and in the center is a massive object. In my example previously, the cluster itself was acting as the massive object, and the light from the right, where the true light source is going through the massive object and being bent because of that large gravitational pull. So, if you know the radius of a gravitational lensing object, you can calculate the mass of the galaxy behind it. The galaxy cluster, again, acts as the massive object, and this method can help in determining the mass of dark matter present. Is dark matter enough? Is it enough to explain the observations we're seeing in the universe on a large scale? No. The universe is observed to be accelerating in the contribution of known mass, including dark matter, only account for about 1/3 of the necessary amount to give this acceleration of the universe. This is where dark energy comes in. Evidence for dark energy. Two key pieces of evidence I'll describe here: Type 1a supernova and the cosmic microwave background. Large galaxy surveys performed from the late 1970s through the early 2000s were able to measure the mass of the universe and found it to be far too low to be consistent with a flat cosmos. Given the compelling measurements of the geometry of space, it was clear that there was a mystery and the universe contained mass and energy that had not been identified. Type 1a supernova are the best known standard candles across cosmological distances because of their extreme and consistent luminosity. On the left is plotted supernova apparent magnitude and the scale of the universe relative to today. Each data point represents a particular Type 1a supernova, and the best fit to the data is the curve, a flat universe with dark energy. On the right is what happens during a Type 1a supernova. Two normal stars are a binary pair, and the more massive object star becomes a giant, which spills gas onto the secondary star, and the remaining core of the giant collapses to become a white dwarf. And then the white dwarf's mass increases until it reaches a critical mass and explodes. Type 1a supernova eventually it becomes too massive to remain stable and explodes, ejecting all its contents. The recent observations of supernova are consistent with a universe made up of about 70% dark energy and 27% of known matter. Known matter is also called baryonic matter. Another key piece of evidence for dark energy is a cosmic microwave background. The cosmic microwave background is a snapshot of the oldest light in our universe. The colors of the map represent small temperature fluctuations that ultimately resulted in the galaxies we see today. Cosmic microwave background calculations demonstrate that distances to a given redshift are larger than would be expected. Next, we need to look at the large-scale structure. Looking here on this picture, on the left is what we believe to be the beginning of the universe, at least the known universe. On the left is looking back in time, and on the right is present day. You can see the dark ages, the first stars on the left, and then the expansion as you move from left to right. The final component, dark energy, is an intrinsic property of space, so it has a constant energy density. Thus, it does not get diluted with the expansion of space. Expansion is slow afterwards as the universe is dense with matter. As the density of matter decreases, acceleration increases. At the current time, at the right of the diagram shows this increase in acceleration. Now we can attempt to answer the question from the beginning of this presentation. What is the universe made of? The most recent findings show that dark energy makes up about 70% of the universe. Dark matter makes up only about 26%, and normal matter, also known as baryonic matter, only makes up 5% of the universe. And here is a short video summarizing our findings.